Hi all, myself Karthik Vaidyanathan. I'm a computer science postdoctoral researcher at University of L'Aquila, Italy. This work was done in joint collaboration with Professor Henry Muccini from University of L'Aquila. Let me first start by giving a context of this research. We have modern software systems that generate tremendous amount of data and suffers from different architectural challenges, which has to deal with questions like how to ensure better quality of service, how to provide better resilience, and so on. On the other side, the field of AI, in particular machine learning, has evolved over the years and it can be used to solve some of the architectural challenges of the modern software systems by leveraging the data obtained. However, machine learning based systems themselves require better architecting practices. This has led to the emergence of two broad research areas, ML for SA and SA for ML. In this work, we focus on this side of the spectrum, which is about how to better architect machine learning based software systems. Then the question is, how is it currently done? So the figure shows a high level view of a machine learning based software system and how a modern software architect perceives such a system. As we can see, there exist two different subsystems, the machine learning subsystem and the software subsystem. On the machine learning subsystem, it's about data, algorithms, and the models. And on the software side, it is about components, connectors, and their relationships. The software subsystem produces the data required for machine learning subsystem and consumes the models that are available from the machine learning subsystem. Now, the next important part is that for each subsystem, the stakeholders and their concerns are also totally different. On one side, it is about data scientists, the data engineers, machine learning developers, ethics expert, and so on. And their concerns are more about how to improve the accuracy of the model, how to version the model, what about the quality of the data, etc. On the other side, instead, for the software side, the stakeholders are more like the developers, the testers, and the DB admin, and their concerns are more related to the functional and non-functional aspects of the system or the technology choice, and so on. So the big question that arises is, do we clearly know how to architect machine learning based software system? Well, in our experience and understanding, this is not the case. So before that, I would like to speak about how we realized that such a gap existed. Back in 2015, we got a project with the famous museum, the Uffizi Gallery in Florence, Italy. Just to give some background, the Uffizi Gallery is the third most visited museums in Italy with more than 2 million visitors per year. There are places within the museum with limited access to public for safety reasons. Now, this museum was also famous for the waiting time. So sometimes people even had to wait up to 4 hours before they could enter into the museum. So the goal that was given to us was to create a software system that could reduce the waiting time of the visitors. To achieve this goal, we first created a big data based IoT infrastructure where we used different types of IoT devices to collect various types of data. This data included the data on the movement of people into the museum, outside of the museum, and within the museum. We then leveraged these data using different types of machine learning models to predict the amount of people that could enter into the museum in a given time slot. For this, we also took into consideration the human factors. For instance, the pattern of visits by a group of people in a museum can be different from a pattern of visit for a family or that of an individual. Also, specially abled people or old people have to be given different priority. So all these aspects had to be considered. So as a result of our efforts, we were able to create a software system that could reduce the waiting time from hours to just few minutes. And as you can see from the image, how the queue has been reduced before the system was deployed and after the system had been deployed. And this attracted a lot of attention both from the national as well as the international media. However, during this process of software development and even after the process of development, we realized that there is a lot of things that we miss in literature as to how to architect a machine learning based software system. Based on this experience and our expertise, we identified four main areas of software architecture that requires better attention both from the research as well as from the practitioner community. This includes architecture framework, architecting process, self-adaptive architecting, and architecture evolution. Let us look at them one by one. Let us first look at the architectural framework. So architecture framework is targeted towards a community of stakeholders or for a specific application domain. So going back to the figure that I had shown in the previous slides, we know that in a traditional software system, the stakeholders and concerns are totally different to that of a machine learning based software system. Now, over the years, different architectural frameworks have evolved, and we can take example of one of the most popular one, which is the 4+1 view model. Now, if you see this architectural framework, there are different views to capture the concerns of different stakeholders. Like we can build use case diagrams to capture the scenarios. Then we can capture the dynamic aspects of the system using the process view by us using sequence diagrams. And this goes on. But in the case of a machine learning based software system, we may need something like this to capture the concerns of the stakeholders who are more from a mathematical or a cognitive science background. This includes people like data scientist, ethics expert, and so on. Then in that case, we might need something like a learning view to capture the learning algorithms and their interactions with the software components. We may need a data view to express the quality of the data, the quantity of the data, the types of data we need, and so on. So going back to the Uffizi experience, we had multitude of stakeholders ranging from IoT experts, statisticians, operational researchers, software developers, and the list goes on. And each of their concerns were totally different. So we had CAPS modeling framework to model the IoT architecture by modeling the space part, or the software part, and the hardware part. However, we didn't have any framework to capture the machine learning concerns. So we believe the way forward for the community is to first identify how to define an architectural framework for machine learning based software systems. Or rather, if there is a software system that has been built using a particular architectural framework and you need to integrate a machine learning based system which is built using another architectural framework, then how do you establish correspondence rules between the different architectural framework? Similarly, if suppose we want to integrate machine learning to a legacy software system, is it then enough just to add additional viewpoints to the existing framework that is already used by the legacy system to capture the machine learning part? Okay, so the second area that we want to focus about is about architecting process. So the first step of architecting process is the architectural design. As we have already seen, we have the software subsystem and the machine learning subsystem. So where should we start the architectural design from? Should it be the software or should it be the learning part that drives the architectural design? The second step of the process is the architecture analysis. So traditionally, we make use of queuing networks or quantitative verification techniques to verify systems that exhibit a stochastic behavior. However, here the machine learning model itself has a probabilistic nature. So how can we perform the analysis? The third step is about the realization of the architecture. Most of the modern software development follows an agile methodology. However, machine learning has an increasingly iterative development style, which is not necessarily incremental. So how can we balance between the two different development styles, the development teams, and the organization of the teams? Finally, the fourth important part is architectural representation. So traditionally, we make use of UML diagrams or even simple box and arrow diagrams as we call for representing architectures to business stakeholders. Now with ML, we may need better ways to represent the architecture and how the machine learning process works to a business stakeholder. So in the case of Uffizi, while we had to architect the system, there was this continuous interleave of decisions between machine learning, software, and hardware. For instance, sometimes we may had to collect specific types of data, and that required us to deploy specific types of sensors to ensure that this data is collected. Also, since two different teams work in a totally different way, many tasks had to be linearized. So we had to wait for the machine learning team to finish before the software team could proceed and so on. Then another important thing is that both the teams had to learn some jargons of each other. For example, the same word feature has different meanings for the machine learning team and the software team. In essence, we felt that there was no systematic process to ensure smoother working of the team or for the smoother development of the system itself. So we believe that the way forward is to address this important set of questions with a focus on understanding how to better create a systematic process to architect machine learning based software systems. Now, the third area is about self-adaptive architecting. So in simple terms, a self-adaptive architecture equips the system with the ability to autonomously adapt the architecture based on different uncertainties. Now, from our experience, In a machine learning based software system, such adaptation can be divided into different sub-areas. The first one is about using machine learning for self-adaptation. As we see in the figure, we could use machine learning on the top of a MAPK loop to predict any uncertainties and then further adapt the architecture. However, machine learning suffers from accuracy issues and hence the decisions made could be wrong. So how do you handle it? The second sub-area is about architectural adaptation for machine learning, where the components consuming the machine learning model could be adapted to guarantee the overall quality of service. For example, as we see in the figure, different machine learning models could be used for the same purpose, but they might offer different metrics in terms of accuracy, CPU consumption, and so on. Then the architecture could have mechanisms that can enable components to autonomously switch between the different models to ensure that the global quality of service is satisfied. The third sub area is about architectural adaptation of machine learning. As I said, machine learning suffers from learning bias and accuracy. This means that during runtime, we can have mechanisms in place that can allow adaptation of machine learning architecture, maybe by adding a few neurons or removing some layers of neurons or by tuning hyperparameters and so on. So in our system developed for Uffizi, we were able to clearly see the importance of the first two sub areas that I had mentioned. For instance, we had developed machine learning models to forecast when to open and close the kiosk automatically. However, sometimes due to accuracy issues, this may not work well, and then we had to manually reconfigure. Second, sometimes we were using computationally intensive machine learning models, and it was affecting the overall performance of the system in terms of the response time. And then we had to place additional constraints on the software component to ensure that such delays do not happen. So in a sense, what we noticed is that there is a need to come up with robust mechanisms to handle these kind of self-adaptations. So the way forward is then to answer this set of questions, which concerns with how we can improve the robustness and trustworthiness of machine learning, which is of course a global problem. Then how to autonomously adapt the models to guarantee overall quality of service, and further how to adapt the machine learning process itself. The fourth area, or the final area, is about architecture evolution. In our experience and understanding, the architectural evolution for machine learning based software system can arise from two main sources. First is the data induced evolution. As time progresses, machine learning might require more qualitative and quantitative data or different types of data to improve accuracy. And this may call for an evolution of the architecture to add additional components to satisfy these kind of requirements. Similarly, evolution can also arise from machine learning models. For example, what you see on the right side is the result of the image classification from a prominent cloud-based vision service in November 2018 and in March 2019. For instance, the first image was classified as skiing in 2018, and in 2019 it became snow. So similar is the case with other images. Now imagine using this as a base to make some kind of decisions, or you might have software components that uses this classification to make some kind of decisions. And it may completely be wrong with time. This means that components consuming the model also need to evolve to handle such changes. So in Uffizi, we generated museum-specific machine learning model with a very small error rate using the data collected for 2 years, and then the model was operational for 20 months on free Sundays. Now the COVID situation will change the way in which people enter the museum once the museums are reopened, and this may mean that we may have to collect additional data or add components to collect different types of data to improve our model. We believe that as a community going forward with the increased amount of machine learning based software systems emerging, we may need better mechanisms in place to handle architecture evolution. We will be required to come up with techniques that can enable architects to take informed decisions with respect to handling evolution. So concluding, the important message that we want to convey is that future software architect will have to be more like an ML aware software architect, where they can at least understand the basic nuances of data science, machine learning fairness, ML ops, and so on. And then we believe there won't be the existence of two different subsystems, rather it will be more a unified view. So future work include, but not limited to, expanding this study into other areas of software architecture, which we had not considered in this work, like architectural technical depth, architectural quality, and so on. We also plan to investigate deeper on the different research directions that we have presented. We also believe that we may have to come up with new architectural style for machine learning based software systems. So I hope you enjoyed the presentation. Thank you, and looking forward to your questions.